we are going to do carbon dating. You heard it, I'm sure you've heard of carbon dating. Basically, so we have two formulas that we use. For half-life, and this one's telling us the half-life, right, 5,600 years. For half-life problems, we're always going to use A equals P 0.5 to the T over the half-life. So I want to give you that formula. So for the other ones, we use PERT. We'll go back to using PERT for the very next question. But for this one, we're going to use A equals P 0.5. What's the 0.5? It's the half. It's the half. Are we good there? Is that making sense? That's a special. You want to put that on your 3x5 card to use on the exam we take in 2 weeks. Yeah, Tristan.
You already answered my question.
There it is, huh? In 2 weeks. Yeah, 2 weeks from today is our exam.
It's to the T, right?
Yeah, to the T over half-life. That's a fraction. T over half-life, yeah. So in our particular case, it's in this particular problem, it's going to be A equals P 0.5 to the T over 5,600.
Wait, do we derive that?
Yeah, that I derived it last time from doing the part 1, where you plug in the stuff. I can show you again later if you want to see that. Come grab me after class. I can do it real quick for you. But I'm just going to move ahead. So there's two formulas we use for if they specifically give you a half-life, then use this one. The 0.5 is the half. That's the half right there to the T over the half-life years. And we'll just use that in specific. If they don't give you half-life, then you use PERT. They're both on the board here. So you use PERT if they don't give you half-life, the 0.5 one if they give you the half-life. Okay, so they're giving me the half-life. This will be our last half-life problem, then we'll go back to the normal PERT. So, all right, so how do I do it? They're telling me the piece of wood has 76% of its original carbon-14. So this is carbon dating and how it works. Living things, plants, animals, people, living things, when they're alive, they keep their carbon-14 levels stable. The minute the living thing dies, the carbon-14 starts to decay, starts to break down. Decay sets in, and the carbon-14 amount starts to break down. And we know the half-life of carbon-14 is 5,600 years. It's got a very high half-life. So that's like a time clock. The minute the thing dies, the carbon-14 starts to go down. So if we find out how much, something that's been dead for a while, if we look at how much carbon-14 it has, then we can find out how much it's gone down, and we know how long it's been since it died. That makes sense? That's carbon dating. So that's what we're going to do here. It's exponential equations. So, all right, let's do it. So they're telling us we got the basic setup already. So this is nice. We don't have to do, remember with PERT, we normally do part 1 and part 2? Well, this allows us to cut right through part 1. It's over. We're ready to just finish the problem for the half-life. That's the convenience of that half-life formula. So it's telling me the piece of wood has 76% of its original carbon-14. So what do I do with that? Remember in the formula, the A is always the amount later, and the P is the starting amount, right? P, like for the banking ones you just did last night's homework, right? The banking ones, that was the principal investment, the first amount put in the bank, and A was the amount later. Same thing with populations and substances. P is the amount at the start, A is the amount later. So, okay, so what do I do with the 70? The piece of wood has 76% of its original carbon-14 left. Becca, what do you think?
The amount later is 0.75 and the starting amount would be 1?
We could do that. 0.76, yeah. 0.76 and 1. That would work beautifully. Let me just explain with the P, though, but that's a perfect plan. That'll work great. Probably, it might even be more sensible to you if I made it 0.76 P and P. How about that? But you're right. The very next step, I'm going to divide out the P, and it'll be 1 and 0.76. Does everybody see that, though? I say all that because one of the things I've seen over the years that's messed people up, let me go back and show you. Here's what I've noticed students do over the years that gets them messed up. So let me say it in specific so you don't get messed up by it. Is I've had students read a question like this. They know the formula. They write it down. I've seen it on their work. And they'll put in the A is 0.76. and they will forget to put in the 1 for the p. They'll just say, well, that's just p, because they're not giving me, the original, and the a is 0.76, and then they stop here, and because they don't have a p on both sides, they're kind of stuck, and then they don't know what to do about the p, and they can't get the rest of the problem, and they're kind of stuck. So with that in mind, that's why I want to help you remember that. What if I just said to you all of a sudden, hey, the other day, 76%. That'd be a weird way to talk, huh? You'd be like, what would you say to me if I said, hey, 76%? Of what? Huh? You'd say 76% of what, Mr. Heron? There's no such thing as 76% alone. Exactly. So there's no such thing as 76% alone. It's always a percentage of something, isn't it? Right? Percentage is a part, isn't it? Like, let's make sure we're really clear on it. What if I said, hey, at the ball game, baseball playoffs are on right now. I was watching the ball game the other day, 50,000 people, 76% had hats on. So now what does that mean? If 50,000 people, you don't have to calculate big numbers or anything, but I just mean, what does that mean? If you describe that to a kid or something, 76% of the huge crowd had hats on. Does that mean 76 people? No, it doesn't mean that. You know that.
3/4 of the crowd.
Yeah, it means 76 per
50,000.
per every 100.
Oh, yeah.
Right? Percent means per 100, doesn't it? 70. Even think about the word. It's percent. What is cent? How long is a century? 100 years. Yeah, and the symbol has what? 2 zeros. Dividing by 100. That's what that symbol means, huh? So if I say 76% of the crowd, I mean if you took that crowd and you broke up the hat wearers evenly, in every group of 100, you'd find 76 hat wearers. Right? It's 76 per every 100. So my point is, percentage always has to be of something, doesn't it? So there's no sense in 0.76 alone. It's 0.76 of p. And then if you do that, the p's drop out right away, and you're good. Or you could just put a 1 on the other side, same thing. All right, let's solve it from there. Let me go to a fresh screen. So we have 0.76 is, what is it? 0.5 to the t over 5,600. Good to there now? So now we need to solve for t. Now, this is where I want to help you and be real clear on two things. Number one, if you want to get the letter out of power, ln both sides, huh? So if you want to get the letter out of power, you ln both sides. Is that what I want to do here? Absolutely. No, I want to get that t down. I'm trying to solve for t, huh? So I want to get it down. Now there's another case, which we'll see in a few minutes, where you just want to get rid of the number. That's coming. And that'll be a little different. But yeah, this time I want that t down. I want that whole power to drop down. So it'll be t over 5,600 ln of 0.5. Are we good there?
Divide by ln 0.5.
Yeah, so to get t alone, yeah, good job. So we want to get t alone now. T's out of power, it's much easier now. Now divide both sides by ln 0.5. So this will be ln 0.76, ln 0.5. Good. And what's the last step to get t alone?
Multiply both sides by 5,600.
Yeah, multiply by that 5,600. Boom. T, and then just use your calculator. I'm getting 2217. That tree is 2,000, or died 2,217 years ago.
Really? When we put it in our calculator, we would have the parentheses around both.
LNs?
Yeah.
Yeah, it automatically does that on most calculators. Yeah, that's right. You guys getting that okay?
Yep.
Am I coming out? If you have any trouble with the calculator, just grab me after. Probably just 1 minute I can help you. Probably just one small thing or something. So I encourage you to bring your calculators and do these. Make sure you can get these numbers. So we good there? So half-life, able to find out how old something is.
No.
on the carbon 14.
I keep getting 23, 40.
All right. Okay, so there's the question. So chlorine decays like any other chemical. So we're just saying the chlorine level starts off at 2.5. 24 hours later, it breaks down to 2.1. So what's the chlorine 3 days later? What's the chlorine 3 days later? 72 hours later. Bless you. So, all right, so this is exponential growth and decay kind of problem, right? We have a chemical that's decaying. Now, there's nothing in here about half-life. They never say half-life, so I'm not going to use the half-life. I'm going to use the pert.
I was going to say, just assume that it decreases by 0.4.
It does decrease by 0.4, but nothing about half-life in here. So, all right, so we're going to use the pert. Now, remember how we use the pert? We got to do it in 2 phases. Remember, we did one of these before. First, the first order of business is to find the e to the r. Do you remember that? It's kind of weird. It's kind of a little bit of a strange way. It actually makes the numbers easier.
Oh, that's right.
We good? Okay, so now let's start plugging stuff in. So the chlorine level is at 2.5. Where am I going to plug that in? Where's that 2.5 go?
That's a rate.
That's the,
Oh, that's expensive.
yeah,
Is that the chlorine level now or later?
now.
Now, the chlorine starts at 2.5, and then later it drops because it's decaying, right? It's going away. It goes down 2.5. So that's the P. We all good with that? Because the P is always the now. The A is always the later, huh? Like with the money. Principal now, amount later. Good, good. Exactly. So the 2.5 is the P, e to the r, and what's the 2.1? That's the later, the A, and the T, that's 24. 24 hours. We'll go with hours. They're going to ask us hours later, so I'll just go with 24 hours. Yeah. So 24 hours later, when time is 24, the 2.5 has gone down to equal 2.1. So the amount later is 2.1. Good to there? So now, what are we supposed to do? Find e to the r. And then after we do that, the second part will be to finish the question. We do these in 2 phases. So the first part is we've got to find e to the r. Let me circle it for clarity. We're trying to find e to the r. So what should we do first? Yeah, divide by that 2.5, exactly. On both sides. And we get e to the r 24. Use your calculator. 0.84. Good to there. Okay, now is everybody tracking close here? Because here's something kind of weird. Am I going to do ln? Let me write a note of clarity. The answer is no, and here's why. So remember what I wrote earlier. Remember I wrote right back here. If you want to get the letter out of power, ln both sides. If you want to get the letter out of power.
You don't want to get r out of power.
Right. See, I want e to the r, don't I? I want that r to stay. See?
Oh, so
I don't want that r to come down.
You're going to multiply by 1/24.
Yeah. So when you only want the number gone, then 1 over number both sides, huh? Because I just want that 24 to go away. I don't want the r because I'm trying to find e to the r. I want that r to stay up there. I don't want it to come down. Everybody see the difference? Back here in the last problem, I had a t up there in the power, see at the top? And I wanted that whole thing down because I'm trying to solve for t. So I ln'd, right? Because ln, natural log, brings the whole power down. But on this one, I want the r to stay up there in power. I want e to the r, right? That's why that's kind of a weird thing and why I'm calling your attention to it. It's kind of weird that we want r to stay up there on that.
Why do we want r to stay?
It's just simply convenience. That's a good question. If you could do ln on both sides, the r would come down, you could solve for r. What it would is you just get a big, long, messy decimal. you'd have to round it, and then you'd have to use it in part 2, and it's just more mess. It's just simply more mess and less accurate because you have to round. Yeah, so simply for convenience. Be glad to show you that in office hours. Somebody asked in the last period, and I showed it. It took too much time. I didn't get to other things. So I'm not going to show it again. But come to office hours. I'd be glad to show you exactly what that means. So for convenience, we're leaving the r up there. So if I'm going to leave the r up there, and I'm just going to get rid of the 24, I'm going to do 1 over 24, 1 over 24, and those will cancel.
Okay, actually I have another question.
Yeah.
How do you know where you're supposed to leave like the r up there, like based off the equation, like if you're going through doing, how do you
PERT. So whenever you're doing the PERT formula, so the last one we did the half-life, right? The last one we didn't do PERT, we did the half-life. Yeah, so whenever you're using the PERT formula, you're going to leave the r up there.
Okay.
Yep.
So if you want to solve
Unless they
just
ask
for
for rate or something like that, right?
Oh, sure. If they ask for rate, then you got to get it down. Yeah, you're right.
So if you want to solve just for r, now you would ln both sides?
Yeah, but I don't want to solve just for r.
Okay.
Yeah, you're right, though, if I wanted to solve just for r. I'm just finding e to the r. It's just for convenience. I know it seems kind of weird. It's just for convenience. So now, let me show you how it's convenient. Now we're ready. Second part, let's finish the question. So how do you finish the question? Well, let me write PERT. And the p is still what it was, 2.5. Now, e to the r. What is e to the r? It's this, yeah, this 0.84 thing. 0.84 to the 1/24th, and then there's the t. Everybody seeing that?
Mm-hmm.
So we plug in
3 days?
the
With
same
72
numbers.
hours.
We plug in 2.5 again, and then our e to the r that we know already.
Yeah, this e to the r, and then the t is still there.
The t is still there, and then 1 to the 24th.
Right, because that's all e to the r.
Yeah.
E to the r is all that.
E to the r. You don't
Yeah.
solve for that. You don't like put that in calculator.
Right, no, just leave it. That's because it's convenient. Yeah. Yeah, we just want to leave e to the r as the 0.84 to the 1/24. That we see why, because we're not rounding anything.
Right.
So it's more exact, and it's easier. There's just 2 decimal places. Whereas if you found r, you'd have to ln, big long decimal, you'd have to round it, be inaccurate, messier. So this is for convenience and accuracy. We just leave e to the r as 0.84 to the 1/24. And then we start again with the PERT, and now we plug in e to the r as 0.84 to the 1/24, and the t is there also. Now let's do one more thing for convenience. What is 1/24 times t? That t is t over 1, isn't it? And so we can just put it on the top. They're just multiplied. So just put the t on the top. Make it t over 24. Does everybody understand? Because t alone is t over 1. It just goes to the top.
Oh, okay.
They're just 2 fractions multiplying. 1/24 times t over 1. So just put the t on the top. It's more convenient. Make that a little bigger there. So there it is. So now we're ready to finish the problem. What's their final question to me? 72 hours later. So I just plug in right there 72 for t. And just hit the buttons on your calculator. I'm getting the amount of chlorine to be 1.48176. There it is. That's the amount of chlorine, the parts per million is what it is. 3 days later, 72 hours later. Does that make sense? You able to get that on your calculator when I plug in that 72? Is that good? Questions on that one? All right, they're going to ask me one more question. They're going to say, when will be, so that's like part A, it's kind of like part A. And then part B, they're going to say, when will the chlorine level, when will the chlorine level be 1.0? That's when they need to shock the pool again. How long till the chlorine level is 1.0? So this is where I want to point out, you know this formula we have right here? Oops, I went too far. The 72 is plugged in. That formula right there. That's what we're going to use for any questions they ask. Once you get that formula, you see, once you've got the e to the r and you've put it in, that's your formula that'll work for any questions they want to ask you. So I'm going to use that one again. So it's going to be A is 2.5.84 to the t over, what was it, 24? So that's the formula I'm going to use for anything they want to ask me. So does everybody see how these PERT ones work? So these PERT ones, you have the part 1 where you find the e to the r, put that in. Once you've got that, then you're ready to answer any question from that. So, okay. So now they're saying when's chlorine 1.0? What am I going to do with that 1.0?
It's going to be the A.
Yeah, that's the A. That's the amount later. Huh. So that's 1.0. It's 2.5.84 to the t over 24. Okay, can you solve that for t now? They said when. They want to know time. So let me give you a second. Can you solve that for time? So what do I do first to solve for time?
Both sides.
Well, first you got to get rid of that 2.5, right? Yeah, we always got to get the base alone, the 0.84 alone. So then divide, yeah. So divide by the 2.5 first and then ln. So what is that? Oops. I'm getting 0.4. That one is 0.4. So 0.4. Yeah, now I am going to do ln here. Does everybody see why I'm using ln now? Because I do want that t to come down. I'm trying to solve for t. Everybody, so basically the only time you don't do ln is that part 1 of the PERT. Right back here, part 1 of the PERT, I didn't want the r to come down. I just did the 1 over 24. That's the only time you're not going to do ln. All the other times, pretty much ln. So I'm going to ln both sides. The whole power drops down. I get ln 0.4 is t over 24 ln 0.84. We get to there. Solve for t. What do I do first to solve for t?
Divide ln.
Yeah. Divide by that ln 0.84. Like that. Good. Come up here. So I get what? ln 0.4 over ln 0.84 is t over 24. And how do I get the t alone?
Times
Times 24.
24.
Boom, cancels out. T equals, and crank that out on your calculator.
I got 126 hours.
Yeah, 126 hours until
5.26
0.1. I don't know what they want there. So 126.1. I don't know how far they went around. Hours until the pool chlorine level drops all the way down to 1.0. Yeah, so good. That's what they want, the nearest 10th. Good? Questions I can answer? You okay with the whole PERT thing and the half-life thing? So we won't do any more of those. That's all the PERTs and the half-lives. But there will be one of each of those on the exam, 2 weeks from today. They're both valuable. All right, so let's, if you're okay, I'll move on. Let's talk. That's an exponential equation, isn't it? So we're using that for the growth of populations and the decay of chemicals and the growth of money. So it's exponential growth. What does that mean, exponential? What does the graph of an exponential function look like?
It goes up really high.
It rockets up, doesn't it? It rockets up. So it rockets up to the right. So that means populations rocket up, do they? Is that what happens with populations of people and animals and things, so they rock it up? Well, in certain circumstances, yes, they do. Do you guys have your phones with you? Could you type in, somebody got on Google? Could you type in, what is it, 24 rabbits, Australia, what's that?
The problem?
Oh, is there like a math question? No. Yeah, maybe, what does it say? Is it a
European rabbits were introduced and released
24 rabbit?
24 wild rabbits
I'm gonna say with
in October of 1859.
October of 1859 on an island in Australia? Is that what it was?
Yeah,
24 rabbits, right?
yeah.
They were going to do it for sport, weren't they? Didn't they want to hunt them or something? So back when they were first, when we were first to have the ships to cross the big oceans, the Atlantic and the Pacific, they grabbed rabbits, and this happened a few different times, things like this. They grabbed animals and they would transport them from one place where they naturally lived to some place they hadn't been before. And when they introduced them sometimes to some other places, if there weren't predators there, crazy things happened. And so that's what happened in the story in 1859.
They released viruses to kill them, and then they just created stronger rabbits.
Oh, really? They tried to.
It says so many bad ideas when they do stuff like
That's
that.
so interesting. I didn't know about that part.
And then they also have mouse plagues over there, where like the ground is like literally covered in mice, and like they're like in the grain silos, and like you step on them as you're walking, they're like bugs. Like there's so many mice. It's
Wow.
just,
Yeah. So anyway, this equation
spiders, giant snakes.
is
Everything will kill you.
uninhibited
Never going to Australia.
growth. So this formula is for uninhibited growth. What do we mean uninhibited? No predators and plenty of space and plenty of food. Plenty of space and food. So that's called uninhibited growth. Now, that's been experienced a few times in history, like you're reading about. So if they brought the rabbits to this new island in Australia, I think they brought them for sport at first. They thought they would hunt them, and the rabbits won. Basically, there was no natural predators on that island. There were no, what eats rabbits? Like hawks and foxes and coyotes and things like that. There was none of that on that island. So they dropped the rabbits, and there was plenty, it was like farmland there in Australia. And so the rabbits had plenty of space, plenty of food, no predators, and they just went wild, and they just grew and grew. I think we saw the numbers last hour. I was looking at the numbers. They were dropping off in 1859. By like 1920, I think there were over 1 billion rabbits were on that island. Yeah, I didn't know about the viruses. They tried taking them out with viruses.
Yeah.
They hunt them with ferrets.
Ferrets? Is that?
Yeah.
Oh, they released ferrets to.
Yeah, which probably caused another problem.
Yeah.
Have you, the wolves, where they took the wolves out of Yosemite?
I heard about that.
That's an amazing video.
Oh, I didn't know there's a video. I just heard about it last hour. Somebody mentioned it. Yeah. So they pulled out the wolves, and the elk population grew too much.
Yellowstone. Yeah, that was Yellowstone.
Was it Yellowstone?
Yeah.
And then so they reintroduced the wolves to keep the elk
And it
population.
changed the course of rivers.
Yes, it
Really?
is. That is true.
Yeah,
I did a report
it
on
changed
this.
the
It's like
course of
10
rivers
pages.
because the beavers came back in. After the wolves came in, the
So-
elk started disappearing. The beavers came back in because there was more trees, and then the beavers changed the course of the rivers, and so
Aquatic
it
came
changed
back.
the entire topography. of
So
Yellowstone
interesting.
National Park.
Everything's all in balance and related. Yeah. So this formula. So remember, math is made up to describe things that are real, right? So what is this formula made up for? This formula is in those situations where growth is not inhibited, uninhibited. When there's plenty of food, no predators. We've seen that a few times in history. Yeah, the rabbits got up to 1 billion. They would come up over the mountains like locusts. The rabbit, they would come, they would just mow. They say the stories. They would just see the rabbits coming up over the hills, and they would just tear out a whole farmer's field in a matter of hours. So they were just destroying the land, and yeah, they eventually, I don't know what they did to take them out, but it had to be massive effort.
No, it's still a problem.
Is it still a problem?
It's still a problem.
All right. So now, when there are predators, when growth, so that's not typical. More typical is there's predators, there's limited space, and limited food. So that's what the new formula is for. This one right here. This is called the logistic growth model. This is number 8. So it's, let me write it first, called the logistic growth model. So remember, math is just made up. So so they say, well, if there's limited things, then here's a better formula to predict how things are going to go. So what is that, 31.45? 31.45 e to the minus 0.47 t, I think. Yeah. Okay, that's called the logistic growth model. So in other words, that is for limited space and food and predators involved.
Limited resources.
Yeah, limited resources and predators. So that models, remember, a model is just a math made up thing to describe reality. So biologists just look at what's really happening and they say, hey, we need a math formula that will fit what we've seen that we can then use to predict the future. So that's what. So if things are limited, they use the logistic growth model. That fits reality better. If things are unlimited, they use the PERT, exponential growth, uninhibited growth. So all right. So they're just going to ask us a few questions now about the logistic growth model, how it works, what are some different parts to it. So let me tell you. Well, probably I should. Let me just. After all that, I'm going to need to put it on a new screen. P equals 8,000. Let me just rewrite it here for you. 1 plus 30, what was it? 31.45 e to the minus 0.47 t. Okay, so how does this thing work? First question, they're going to ask you, what is the carrying capacity? Carrying capacity means what's the capacity of the environment? The environment's capacity. So the environment's capacity, like how many rabbits can it hold? If this is rabbits, I don't know what this represents here, but what can? Oh, it's bacteria actually. That's right, I do know. Number 8's about bacteria. So if you have like a dish that the bacteria are growing in, like a petri dish, right? And you're growing some bacteria. So then what is the carrying capacity? Well, it's the number on the top. So it's that 8,000. So basically the number in the top is how many that the environment can handle before overcrowding starts to set in and they start dying off because there's too much.
Or jumping off cliffs like lemmings.
All right, and then B is going to ask us, what is the growth rate? So what's the growth rate? Yeah. Yeah. So yeah, that's right. It is. Yeah. So I'm just saying when a biologist, so they would look at a real life situation and they would say, hey, we've noticed that, this petri dish can hold 8,000. After 8,000, the things start dying off. So that's the number they would put in the top. So the way this works in the real world, biologists would watch what happens in real life with the dish or the field for the rabbits or the forest for the deer or whatever, and then they would make an equation that fits that reality, and what they put on the top is the maximum amount the environment can handle. And then what's the growth rate? What do you think? It's just like PERT. Just remember PERT.
Would it be e to the negative 0.47?
Yeah, it's right there, huh? But it's positive, not negative, so it's actually positive. They want a percentage. 47%. Now, why is it positive? Well, it's complex. This formula is a little more complex than the PERT. It's because you think, well, yeah, but it's negative there. Yeah, but it's negative on the bottom of a fraction. Yeah. Negative on the bottom means it's actually positive. I don't want to go into any more detail than that. Basically, we're not biologists, so, but we might be, and you'll study more if you become a biologist at that point. So basically, it's positive because it's negative on the bottom of the fraction. So that's where you put the growth rate. So if you notice, then after every year, or every whatever, in this case it's bacteria every hour. If you notice every hour the bacteria population goes up by 47%, that's what you see with your data, then you would put a negative 0.47 right there in the bottom, and that would make the math do that, is what it's saying. Next question, they're going to say, what's the initial amount, right? Yeah, what's the initial population? So part C, initial population. So how many bacteria at first?
0 or 1.
So how do we find out for any math formula representing things in real life? How do we find out the initial amount? What do we do? So initial means time 0, right? Because at the start, time is 0. Yeah, so whenever they say initial, they want you to plug in time 0. So just take that little formula and plug in time 0. So the population will be 8,000 over 1 plus 31.45 e to the 0, huh? When I plug in t 0 there, that whole 0 times negative 0.47 is just 0.
So that'll just be 8,000?
Well, what's e to the 0?
It's a 1.
1. So this will be 8,000 over 1 plus 31.45 times 1. So that's just going to be 32.45 on the bottom. Just 8,000 divided by 32.45. I'm getting 240. I think they want you to round nearest whole number. 247. Yeah, 246.5. So it rounds 247. So 247 bacteria initially. That's how many bacteria started in the dish initially at time 0. We okay so far? It's making good sense? So initial always means time 0. Time 0 on that. And then next question, they're going to say population after 8 hours. You could do that. Let me jump down to F. That's the hardest one. That'd be the most useful for us. Everybody good to there? A, B, and C. D asked, 8 hours later, you just plug in 8. I don't think that'll be a problem. Well, yeah, let's jump to F. That'd be the best. So on F, when will the population reach half its carrying capacity? When will the population reach half of its carrying capacity? Let me write the formula again for us. 8,001 plus 31 point, what is 31.4 of e to the minus? Yeah. Okay, so when will the population reach half of its carrying capacity? So how am I going to find that out? Jumping right to the last one, the hardest one.
Well, 4,000 for
Good.
the capacity.
That's right, because the total carrying capacity is 8,000, half is 4,000. Where do I put that 4,000?
On top.
I put that in for P, right?
Oh.
Because you want the you're saying when is the population going to be 4,000? So half the carrying capacity is 4,000. Plug that in for P. Good to there. Now, how do we solve for T? That's a tougher one. Trying to solve for when, right? When is time?
Well,
T.
you could multiply it by everything on bottom.
Yeah, or how about the same kind of thing? How about we just go over 1 and cross multiply? Same thing you're saying. Yeah, it'll be the same result. Good. Yeah, when you got a fraction on one side, whole number on the other, just put it over 1, diagonal, diagonal. Just cross multiply, that good? So we'll have 4,000 times 1 plus 31.45 e to the minus 47t is 1 times 8,000. We good? Good to there? And then distribute that 4,000. So boom, boom. So we get 4,000 times 1. And then 4,000 times that 31.45. I'm getting, what's that, 125,800 e to the minus 0.47t is 8,000. We good to there? Trying to solve for t still. What should I do?
Divide by 125,800.
Maybe you're a step ahead. So we want to first subtract that 4,000, yeah, and then we'll divide, huh? So do that. Bless you.
That's you.
And then we divide by that 125. 125,800. Boom, boom. We're almost there. I'm going to go to fresh screen. If you're okay to there. Everybody getting that copy down okay? So we're getting e to the minus 0.47 t is 4,000. 405,800. We good to there? Then if you divide that in your calculator, I think you get something ugly, don't you? But that'll be fine. So e to the minus 0.47 t is 0.0317965024. Okay. So what do we do now to solve for t? Am I going to do ln? Yeah, because I want the whole t to come down. So you pretty much always do that ln except for the part 1 and the pert, where you're trying to just get, that's just the weird time we don't, right? Pretty much all the other times, totally. ln, because you want the whole power to come down. Minus 0.47t ln e is ln of 0.03179650024. ln of e is 1. Last step to get t alone.
Divided by 0.47.
Negative 0.47. Boom. T equals. And see, I just leave it on my screen right now on my calculator just to make this easy as possible for you. I have the 0.03 blah 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 number, and then I just hit ln of answer. I use the answer button all the time. It's really convenient. I just hit ln of answer. You know where the answer key is? At least on the TI, it's at the bottom above the negative button. Hit second, the negative. It's different places on other calculators, usually near the bottom. So I do ln of the last answer equals, and then I just go divide by negative 0.47. So I never have to type all that stuff in. 7.337 hours. I don't know what they want me to round to. But 7.337 hours later. The bacteria will reach half of their maximum. They'll fill up half the dish, basically, after 7.337 hours. Questions I can answer, so I'm going to move on. I think this is probably going to be it for this section. I'll glance at the other ones, but I think that's about it. We good? No questions?
I hate Ferrets.